Hello everyone. Today we are going to focus on solving the zeros or roots of a nonlinear algebraic equation. As far as I know, most of you know how to solve linear equations that are algebraic, and you do different ways to do it. If there are several of them, use Gauss-Jordan elimination method, or you use the matrix format and matrix inverse. But when it comes to nonlinear equations, I found that most of my students need a little bit of instruction, basically. So I always ask in my class, well, let's say if I give you an equation like this, that, for example, x cubed minus exponential negative 2x plus cosine of x squared plus 4 is equal to 0, can you give me the value or values of x for which this equation is valid or holds? And I found that they don't. So there are different methods, several algorithms in the literature for finding the roots of nonlinear algebraic equations. Today I am going to show you 3 of them. And the first one, which is the simplest one, and it always has the convergence. It is a little bit slower than the rest of them, but it has guaranteed convergence if there is a root in any range. Is called the bisection method. So the idea is very simple. If you have a function that is continuous over a range between a to b, and f of a times f of b is negative, which means your function is going to cross the x-axis at some point, then this method, which as I said is slow but definitely finds a root for you, the idea is this. Well, if you give me a and b for which these conditions are valid, I'm going to find the mid-range c, which is a plus b over 2, of course, and find the value of f of c. If it's exactly 0, well, I'm lucky. If not, then the root, let's say here, c is a little bit to the right of this red point. If that's the case, now I'm going to divide my range into those two halves, one from a to c, one from c to b. And again, check this condition is valid for which one of them. If f of a times f of c is negative, means the root is on the left half. If f of c times f of b is negative, means it is on the right half. So now the half that I know has the root, I keep it. The half that I know it doesn't have the root, I neglect it. And again, I go to the side, the half that has the root, and try to find the midpoint again using this algorithm, and keeps going and narrowing down, narrow until the range is so small that the midpoint, the f at the midpoint, is very small number, okay, which you can practically call it 0 depending on the accuracy of your application. So this is an iterative algorithm, and the rest of the methods that we're going to focus today and learn about, they're all iterative algorithms. They are numerical solutions. And we have to have a way to say this loop, this iteration, stops, which we call convergence criterion or criteria. And in this case, our convergence criteria is keep shrinking this range until finally you have something like, if I call this whole thing f of x, so the goal is to find a point x star for which f of x star is 0, but if I can find a point like x star for which f at x star is less than some delta, less than some epsilon, whatever, where this guy is a small number, then I say this is a very good approximation of the actual root, and I would stop it. Okay, so we call it stopping criteria. So the algorithm looks very simple, and here I have written a MATLAB code, and I want to share with you what I did that finds it for any function that you type in with a range, and basically it also animates that as well. So let me show you that. So here is the code that I wrote, and I'll try to share it with you later. And there is no copyright on it. Now, if I'll share it with you later, download it, or if you want to just take pictures of it and write it as your own code, do it. I do not own any copyright on this because I have not made this method myself, so feel free to download, use, and change it as you wish. So here, these are the 3 lines of code you see I always use in my math lab, okay, to cleaning everything, including the screen, the command window, basically, the workspace, and closing all the open windows. Here is the number I consider very small. So this is that epsilon for me, okay? If my value of the function, absolute value of the function at the roots that I found is less than this number, I say it's 0. Now in MATLAB, that's not exactly 0, okay? In MATLAB, if you just say epsilon, any any number below this 2.22 times e to the negative 16, any number below this is practically numerically 0 for MATLAB. So 10 to the negative 3 is not 0 for MATLAB. And we can make this number smaller. The smaller we make this number, the more it takes for the algorithm to converge. And here the goal is to show you that this method works. So I'm not going to make it super small and then wait for a good long time before it converges. Another thing that you need to consider is a maximum iteration. Sometimes, now in this method, you don't really need a maximum iteration because this algorithm, if there is a root, there is guaranteed convergence. So it will converge. But not all of these algorithms we are going to discuss, like the second method next or the Newton-Raphson, they are going to converge. Okay? You start with some initial guess or some initial range, and there is no guaranteed convergence. And they might diverge instead of converge. I'll show you in examples. And if that happens, you are going to be in an infinite loop. The loop keeps going. It will never converge. The numbers are either wandering around or getting bigger, 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 or smaller, smaller. And you will never converge, and you have to just sit behind the computer and wait forever. So you typically provide some maximum iteration number and say while the value of the function is bigger than or equal threshold, and what? The number of iterations, here we'll talk about this II, this is the loop counter, is less than this maximum iteration allowed, keep doing it, keep iterating. But as long as one of these two is violated, the loop is going to stop, okay? So if you converged, which means this condition is not valid anymore, or if you are diverging in an infinite loop or in a very long loop, that shouldn't be like that. This condition is violated, and there is and between them, so one of them violated is enough to stop the whole while loop. So it says, while that is happening, which means I have not converged yet and I have not passed the max iteration allowed, keep doing. What should you do? So here, this is a function, very easy function I provided just to show you. So here is just a quadratic function, and you might say, well, what's so special about the quadratic? I already know how to solve it analytically. I know. I just want you to, since you know the roots of this, right? The roots of this are -1 and -3. So I just want to show you something that you know the roots of which, and compare it against what this algorithm gives you to have a sense of whether it's really working or not. But later I can change this to any function that you would like. And here I'm using inline functions, okay? And I have provided the range of 1 and -2. And you see here, first my algorithm checks, say, hey, if f of a times f of b is bigger than or equal 0, it means there is no 0 in this range. Now this, remember, this is not perfectly correct. You have to say bigger than 0, because if it's 0, it means one of the a's or a or b that you provided is actually the root. So here we say if it is what? Bigger than 0, it means there is no 0 in this range. Now, is that completely correct? No. But here we ask the user to give us a better range. Okay, so if f of a times f of b is positive, it does not necessarily mean your function does not have a root. It means probably the range is a little bit too big or too small. So in this case, let me talk about it. So here we are just being a little bit lazy. We are asking the user to give us a better range. It doesn't mean there is no range. Okay, so this is my f of x, that in this case was x squared plus 4x plus 3. And this is x. And this function, you know, at x of 0, it is at 3 units. So it's here. And then the min happens at negative, right? It's 2x plus 4. It happens at negative 2. If you plug in negative 2, you will have negative 1. So it should be here. And we can add one more point. Let's say if we add, let's say negative 4 here. In negative 4, this is, these two are going to cancel. So you get 3. So you're going to be here. So the function would look like this. It's a parabola. And the roots of that are at negative 1 and negative 3. Now, let's say here, the range that I provided is what? As you can see, the range is negative 2 to 1. So this is my range here. From here, let me make sure. So the roots are at negative 1 and negative 3, right? So it's negative 2 to what? 1. So this is the range I have provided, for which f of negative 2 is negative, f of 1 is positive. So there is clearly what? A root here. So my algorithm should converge to negative 1, and it does. Okay, but now you might say, well, what if instead I gave it from negative 4 to 1? What if I passed it this range from here to here? Clearly, you see f of a times f of b is positive in this case, and you might say, well, there is no root. Of course there is. There are two actually. But here we are being a little bit lazy and say, well, you know what? I cannot guarantee you because, well, you might be, let's say here, let's say you are between negative 4 and negative 6. So your range could be like that. And clearly f of a, f of b is positive here, and there is no root. So when f of a times f of b is positive, there are two scenarios. Either the range has one or several roots, or it doesn't. I cannot guarantee. But when f of a times f of b is negative, I'm sure I would cross the x-axis. So I'm asking the user to provide a better range, just trying to explain what's going on behind the scene. Okay, so here I have a good range, and then I ask the user to make sure it gave me a better range. And then I calculate the mid-range. I start my loop counter. I also store the value of the midpoint, which is supposed to converge to the actual root at the end. I will save them at each loop because I want to do animation later. I also keep the value of the left point and the right point of each range. Again, because I want to do animation. And then I say, while those two conditions are not violated, then go. If f of a times f of c is negative, which means the root is between a to c, then what would you do? If root is between a to c, you're not going to change a, you're not going to change the left side. Keep the left side as is, but the right side, change it to the midpoint. On the other hand, if f of a times f of c is not positive, it means what? It means it could be negative. It means positive, so it means the root is on the right hand side between c to b. Then what? If it's between c to b, basically you have to change a to now be c, and then you have to plug in the value of b into c. And you should not reverse the order of these two lines, 39 and 40. If you do, C that you want to assign to A will be changed to B first, so then you cannot assign it to A anymore. So make sure you write it in this order and end. So here is changing the range side, and then once you change A, B, and C, or at least two of them, what? You store them here with as the next values at the next loop counter. You calculate the mid-range again and go back and check these conditions. See whether you converge or it is diverging. And if it's not, keep going. And finally, the goal is to the C point to converge to the actual root. And let's say if it does or not, how do I check? Because this loop can stop for one of these two conditions violated. How do I know whether I converged or what? I diverged. So this is what I do. I go back here and say if II, which is the loop counter, right? The number of iterations here. If the number of iterations I use to converge is less than the maximum, it means this condition is okay. This was okay. It was this one that was violated, so means I converged, correct? So if my iteration is still within the range, I say, well, after so many iterations, which is here, II, the zero of the function is at point CC, or C here, sorry. If not, I say, well, the algorithm did not converge. And here I have an animation. I first plot the underlying function, and I provide a title for the function using the function itself. And then I do plot 3 points. One is the left point of each range. I do it using a black circle. Then I do the right point of each range. I do it using a red circle. And then I do the mid-range, and I do it using a green triangle. And I keep the name of the handles for these plots so that I can use them in a for loop, and by changing their X and Y data, as I mentioned in the past about animations in MATLAB, I can do what? I can do an animation. So I draw now, I put a pause so that it doesn't go too fast, and look here. So clearly you see the range is shrinking, 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 midpoint is changing, and boom. Now you're converging to what? -1. And here you can see using this legend what is what. Correct? Let me run it one more time for you so you can see it better. So right now the range is big, it's shrinking, shrinking in half, and ultimately I will converge to -1 as expected. Now, how many iterations of this algorithm did it take it? If we go back to MATLAB, you can see that it took about 11 iterations. We started in a range of 1 to -2, and we converged to what? -1. And you know -1 is an actual root in this case. Now, the final root value and the number of iterations are functions of the initial range you provide, and they are also functions of this tolerance. Okay, so for example here, instead of 10 to the -3, if I make it 10 to the -4 or 5, you see the iteration would change. And as I said, if this range does change, so here you know between -2 to 1 there is a root. Now if I say -2 to 0, what happens? Yes, when you find the mid-range between -2 to 0, the mid-range is -1, and -1, you're lucky, it's exactly the root, so it takes one iteration. You see? Or if I say, let's say between -2 to, instead of 1, I say to +2. Now it should ideally take a little bit more iterations, but let's try it. So this time with the same tolerance, some convergence, I change my range a little bit and run it one more time. And you clearly see, maybe you're lucky, maybe it takes fewer iterations. Is it? Let's find out. Yes, 2 iterations. Why? Because the range was symmetric. So first I went from 2 to -2. I went to -2 to 0, and then from -2 to 0, I went to -1. So 2 iterations, right? You see? So it depends on where the root is and where you can find it. Now let's make this 5. Do it one more time. Okay, now it is taking more iterations. Right, and if you can see, now I have 12 iterations. And now for the same range, I'm gonna make the tolerance tighter. So make it 10 to the -6, and let's see what happens. Is that gonna change anything? Now, since I start with integer numbers, there is a good chance that it doesn't affect it significantly, or maybe it does. Let's take a look. So it's still working, you see in the back. I have not gone to the actual solution, so it is still trying to tighten. There we go. Now, after 21 iterations, the solution is -1. Now, pay attention here. This number is not perfectly -1. You see -1 because you're only showing it to what? 2 decimals. If you want to see what's going on behind the scene, what you might want to do is, before doing this fprintf, if you really want to see, you can use this command, format long. Okay, now it will show you a lot better. So let me show you that. Okay, so the numbers that you're getting are not like perfectly -1 in this case. Up to so many decimals it is, but not all the way, all of the decimals. So let's take a look here. So 21 iterations. Okay. Oh, yeah. Why didn't it happen? Good question. Because although I made format long, but I said what? 4.2f. So I did not allow for more decimals to show. So now I'm gonna make this like 10 and 8. Okay, right? Or maybe 10 and 9. Let's say 10 and 8. Now it should give me enough of decimals, and you can see that right now. That is the number that it converts to. Now, why is it taking it a little bit? Because of the animation. It's the animation that is taking it long. Okay, the convergence was quite fast. It's the animation that is time consuming. Okay, if you turn down the animation, this convergence could be quite fast. And you see now, yes, it is up to what? 6 decimals, zeros, and these last 2 numbers are not. Now, if I go back and turn the tolerance back to what it used to be, now you will see that this number, you see, it's only 3 decimal 0. The rest of it is not. Last time, all these 3 others were also 0. Okay, so clearly you see the effect of tightening the tolerance or the threshold. Now, let's look at a couple of other things. So as I said here, the animation is killing the time. If I comment out all of this part, definitely it is going to be a fast convergence. Here we go. Boom. And if I want to know how much time it took it, all I need is to put a tick and tock command, as you know. So a tock here, and then a tick here, before and after the loop, and that will show me how fast it takes. Okay, so as you can see, the time it took it to converge is less than 0.003 of a second, or 3 milliseconds. Okay, and this number is not perfect. You have to take several runs and take the average if you really want to know about the time it takes. Okay, but it's about 3 milliseconds, as you can see. So this is about the animation and about this method. Now, one more thing I want to show you in here, instead of looking at, you see, every time I try to converge, it converges to -1. Why? Because the range I provided was including -1. Now, this time you might say, what if you use the range to the left side of this point, -2? So let's say from -5 to -2. If I go -5 to 2 or -7 to -2, am I going to converge to the other root? And it should be, right? So let's just try it. So here I make this -5 to -2, which includes -3, or let's make it -6. So it takes a little bit more time, but should be very fast. And look, the root is now converging is perfectly -3. Okay, now here -6 is a good number, makes life easier. And here, that's another one. Okay, so, but anyways, you clearly see that it can converge. So you might say, well, if I have a function that has several roots, how can I find the roots? Well, you have to give it several ranges along the x-axis that you're sure there is a root. Okay, so chop the x-axis, especially the parts that you think there is a root. Chop it in several pieces, several ranges for which f of a times f of b is negative, and each time pass one of them, and this algorithm will give you one of the roots. Okay, it has guaranteed convergence. It's not the fastest algorithm, but it is a very good one. So this is called the bisection method that I showed you. There is another method that this one is called the secant method. Secant method, basically, instead of chopping the range in half each time and looking for it, it tries to be a little bit smarter. Why? Because in the second method, in the bisection method, I'm sorry, to find the root, you don't care what type of function you're dealing with. You're not looking at the function itself, the slope of the function, how fast or slow it is changing. All you care is to find a range and then chop it in half. It works regardless of the function. Now in the second method, you try to take advantage of the rate of change of the function, okay? And definitely in the next method called Newton-Raphson method. So what would you do in the second method? Again, here you need 2 points or a range over which f of a times f of b is negative. So there is a crossing of the x-axis. So here, let's say this x0 and x1. There is this root here. Now what you do is you connect these 2 points using a line, and the intersection of that line with the x-axis is going to be your next point. And then now that you have x2, now you go with x1 and x2. So first one you go x0 and x1, now you go x1 and x2. Connect x1 and x2 together, and they will what? They will hit the x-axis at x3. Now you come down to x3, and this time you go between x2 and x3, connect them, and x2 and x3, these 2 points, sorry, these 2 points. Let me do a couple of more iterations of this for you. So you can have a better understanding. So here, now that you have x3, this is the corresponding point for x3, and this is the corresponding point for x2. So now connect them again together. So now this is going to be your x4. Okay, so now you go between what? 3 and 4. So this is 3, this is 4. Okay, and now you connect 3 to 4, so it goes like this. So this is going to be x5, and let's say this function is continuing like this. Looks like a sigmoid function. And then here you go up again, and now go x5 to x4, and 4 was here. So now you treat it like this, and you see that this is x6. If you look at x4 to x6, it's smaller than x0 and x1. But because of the nature of this function, it takes quite some time before you hopefully converge. And it might not converge depending on the type of the function and the curvature of the function. It might or might not converge. So this method does not have a guaranteed convergence, but since it is using the slope of the function, you have sometimes, depending on the curvature of the function, a better chance that you converge faster than the bisection method. Okay, so but no guarantee. So personally, if I want to choose and I'm looking into finding one root instead of several, I would use bisection over this, but again, bisection is not as smart as this. And the update equation for each point based on the previous 2 points is here. Xn is xn minus 2 times f at xn minus 1 minus xn minus 1 times f at xn minus 2 divided by f at xn minus 1 minus f at xn minus 2. Where do you get this from? Let me show you very fast, and then I'll show you the MATLAB code. So here, let's just focus on x0 and x1. So we connected x0 and x1, these 2 points together. What's the equation of this line? So this is here, f at x1, and this point here is f at x0. So if I want the equation of this line, it is going to be y minus f of one of the points, let's say x0, is equal to y2 minus y1, which is this guy, over x2 minus x1, which in this case is x1 minus x0, that's the slope of the line, times x minus x of that point. So this is the equation of what? That line. Now this line will intersect the x-axis. On the x-axis, y is 0, so this guy is 0, and x is going to be your next point, x2. So all you need now is to find x2 from this equation, and clearly you have to multiply both sides by the inverse of the slope and then take x0 to the other side. So if you do that, x2 is going to be x0 and then minus f at x0 times x1 minus x0 divided by f at x1 minus f at x0. Okay, so you can use your equation in this way if you want, or if you are preferring to make it all one single ratio, then what you need is to take common denominator, and here you have to multiply this x0 by the whole thing. Okay, this is for x0 multiplied by that now, minus this f of x is multiplied by that, so this is negative x1 times f at x0, and then here is negative negative, so it is going to be positive x0 times f at x0. And now see if you can cancel out anything, and you can. This term and this term are going to go away, so you will get x2 to be equal to, as you can see here, x1 times or x0 actually, it's x0 times f at x1 minus x1 times f at x0, and then divided by f at x1 minus f at x0. Okay, so this is your equation, and now if you want, instead of 2, 0, and 1, you can make this guy to be what? So you can see here, you can make it n and n minus 2 and n minus 1. So basically you can add to the subscript of each and every one of these the term n minus 2. If you add n minus 2 plus all subscripts, this guy becomes n, this guy becomes n minus 2, this guy becomes n minus 1, n minus 1, n minus 2, n minus 2, and n minus 1, and that is this equation that you will see, this update equation. Okay, so let me show you the code. So here, this is the second method. Structure similar to the previous one. You definitely need the maximum iteration here because this algorithm might not converge. The same function, the same range, everything. Again, asking for a good range. And here, I already set my first 2 points to the left and right points of the range. And then here, I'm using this update equation to go from point 1 and 2 to the new point 3, the new intersection. And then keep using my while loop as long as I have not converged and not diverged. And I'm using my update equation that you can see here. Instead of n, I'm using I, and then I say, well, if you diverged, say it. If you converge, show the root. And here there is the animation code again, similar to the previous one. So here, let me run it for you. You see, first the 2 points which are in black, the 2 points, the left and the right point of the range, were both on one side of the intersection point, which is the red point. And then they changed direction, and now they became on the left and right side. Let me show you one more time. So look here. You see, they were on the left. Now the red point is on the middle. Again, they come on the left, the middle, right? So here, the next point is not always between the 2 points that you start. Sometimes it's outside the range, then it might come back inside the range and keep going, right? And here you can see that with the same range and with the same threshold, it takes 9 iterations for it to converge instead of 11 that I had in the bisection method. So this method is a little bit more smart. It can converge faster if it does, and that is also actually the basis for the next method, which is called Newton-Raphson, and that is the fastest method that we're going to discuss. And in the Newton-Raphson, instead of looking into 2 points and the intersection point, you directly look at the tangent line. But the Newton-Raphson is very similar to the second method, a little bit faster, with some limitations, of course, which we'll talk about. But clearly you can see that this method is a little bit faster. Now the last method, as I called, is called the Newton-Raphson method. Here you don't need 2 points to start, you only need 1 single point, an initial guess, right? Here, let's say xn. And then at the point xn or x0 or whatever your initial guess is, you draw the tangent line to the curve. And then what? It intersects the x-axis. That is going to be your next guess. So now you go at the point corresponding to the next guess and draw again the tangent line, find where it intersects the x-axis. Go and keep going. And basically what you're doing, you're following the slope, the curvature of the curve, the function, until you get what? Close to the root, close enough that you can say I have converged. Now clearly here, the update equation, I'll show you, the update equation is xn plus 1 is xn minus f at xn divided by f prime at xn. This method actually has the fastest convergence. It's very fast, and it has some limitations and some advantages. So advantage, as I said, is fast. It needs 1 starting point, not 2. The disadvantage is sometimes you do not really have an underlying function. You only have a bunch of data points. And so there is no function f from which you can take a first derivative. Okay? The other thing is this division here. Sometimes the f prime at the point that you are trying to find, the current point, is going to be 0. Or in the matrix format, as I'll show you later, instead of dividing by the f prime, you have to multiply by inverse of a matrix called Jacobian, and sometimes the Jacobian does not have an inverse. Okay, which means if you want to divide, it's going to be like division by 0. And that makes this algorithm also diverge. So this algorithm has its own problems, which we're going to talk about in the next slide. But first, let me show you where this update equation comes from and applied to the same example. And then we go and talk a little bit more about some of the limitations of this method as well. Okay. So first, where does that update equation come from? So here, it's not really hard to show. So at any point xn, I draw a line tangent to the curve, right, like this point. If I want the equation of that line, the equation is quite easy. It's y minus the value of the function at the point is slope of the line, and you know slope at any point is the value of the first derivative, times delta x, which is x minus xn. And all I need is now, again, I want the point where it intersects the x-axis. In other words, y is 0, and the next x, I call it xn plus 1. And so from here, I can easily find xn plus 1. All I need is I divide both sides by f prime. So you will get this. And then I take xn to the other side. And clearly this equation is the same as this one if instead of, well, that's exactly this one. Okay, so I perfectly got this one. So very easy. Let me show you now how we use this method. So here, the same function, we need a maximum iteration, we need some threshold. And here, not only I need the function, I also need the first derivative of the function. And here I'm using symbolic toolbox instead of inline functions. So I can easily take the derivative of that function. And here you clearly see I start with some initial guess of 0, right? So here for this function in this root, I'm gonna start with what? With 0. So my guess is gonna be here. The root is actually there. So I start here and we'll try to follow the slope and the curvature and see if I will converge to -1. Okay, and here you clearly see I have evaluated my function, my derivative of the function, and I use my update equation here, and again check whether it converges or diverges, and then I can show you the animation of it. So let's do it. So here we started at 0, and very fast we converge to what? I, correct? X of I converges to 1. How many iterations did it take? 4. So if you remember, for the very same problem, bisection was 11, secant was 9, now this guy is only 4 iterations. It is very fast, way better than the others, okay? And that's what we use in many algorithms for finding the zeros, for optimizations, and so on, okay? You're following the slope. The general multi-dimensional version of this, we call it the steepest descent. Okay, we follow the gradient of the function in general, which is like a generalized slope. So very fast algorithm. Now you might say, well, what happens if your start point instead of 0 is what? Like -5? Are you going to converge to -3? Well, let's try it out. So here I will set my initial guess to -5 and ask it to converge. And there we go. It does. Again, how many iterations? As you can see, it takes 5 iterations and it will converge to -3. So this method works really nicely. Works relatively good. Now you might say, what if you started at -2? What happens? Well, here if I start at -2, the slope is 0, and the line that I draw, the tangent line, is never going to what? Converge your intersect your x-axis. So you're never gonna have a new point. So what happens? As I said, the slope is 0, which means f prime is 0. And what happens to the update equation? Yes, you have a division by 0, so you are gonna get an error. Okay, and that's one of the things you have to pay attention when you're coding, that if for any reason this f prime is 0, you have to stop the code and say division by 0, try another point. And here I haven't done it, but if you are a good programmer, you have to think about it. Okay, so here, look, it says 3 iterations, but it didn't converge to anything. It didn't give me an error for division by 0, but instead gave me a nan, which is not a number. That's the same thing, basically. It did not. So instead of here, I should say, if this derivative or the new value is a nan, stop it. Okay, don't let it move forward, right? So here that you're calculating this derivative, you can add something. You say if this absolute value of this derivative is equal to 0, or you can say it's exactly equal to 0, or you can say it's less than some small number, right? So here I make it exactly 0 because in this case it is. If it's exactly 0, then what? You will say display division by 0, try another initial guess. Okay, and then what? Break, right? Break the loop. So you can do that, and that will take care of that error for you. So make sure you have that in mind. Now, as I said, this method has a few other things we need to talk about. One is, what if you have more than one equation that you want to find the root for? In many applications, you are solving more than one algebraic equation, nonlinear algebraic equation, right? You have to have several of them solved simultaneously because they are coupled. They have to be solved together. So how would you generalize this update formula? So it is very similar, except as I said here, instead of dividing by a single derivative, first of all, instead of a single derivative, you have the derivative of several functions with respect to several variables. So you have what we call in mathematics, we call it Jacobian. And instead of dividing, you have to have what? Inverse of that multiplied by those functions. Okay, and if I want to find the inverse of this Jacobian has to be what? Square matrix. So in other words, if I have 3 equations, there should be 3 variables in it. So my system of equations should not be over or under constraint. If they are, we can talk about it later. We have to use, instead of inverse, what we call pseudo inverse of the matrix. So we'll talk about over and under constraint systems later. But for the moment being, we assume we have enough equations for the number of unknowns, or number of unknowns is the same as number of equations. Okay, and you might say, well, how would you implement that? So I'll show you in an example, and then we talk about the cases that this method does not converge. So let me show you an example of that as well, because I really want you to learn math and like math, not hate it. So let's say here I have 2 equations. The first equation is like x squared plus xy cubed minus y plus 4 equals 0. And the other one is like x plus y squared minus x to the 4 sine of y, and then minus 6 is equal to 0. Okay, so let's say you have to solve for x and y from these 2 nonlinear equations. How would you do that? Well, what you will call this first one f1, or f if you want. You can call it f1 of x and y, which should be equal to 0. And this guy, you would call it f all the way to the end, f2 of x and y, which should be equal to 0. Okay, so now what you need is, since you have two functions and two variables, you have to calculate the Jacobian matrix J, which you show it as partial derivatives of these fi's with respect to x and yj's, okay? Or if you want, you can call them, you know what? I can call them x1 and x2 if you want to make life a little bit easier, but that's okay. So here I assume one of my x's is the x itself, the other x is y. Or again, if you want, I can call them x1 and x2. That makes my notation a little bit nicer. So here I call this x2, and this makes it nicer. So then this is going to be x1 and x2. And similarly, this one is going to be x1 and x2. So here you have something like this, where I is 1 and 2 and j is 1 and 2. So there's going to be this matrix, this Jacobian. So if you expand it, basically, it is going to be like the partial derivative of f1 with respect to x1, then partial derivative of f1 with respect to x2, and similarly partial derivative of f2 with respect to x1, and partial derivative of f2 with respect to what? x2. So if we calculate them in this case, we have, so if you go up here and try to take derivative of f1 with respect to x1, you're going to get 2x1 plus x2 cubed. So let's do that. x1, 2x1 plus x2 cubed. That's one element, then derivative with respect to x2, which is going to be 3x1 x2 squared. And then minus 1. And then you will have partial derivative of f2 with respect to x1, which is 1 plus 4x1 minus 4x1 cubed. So 1 minus 4x1 cubed times sine of, I guess it was x2 square, x2 itself. And then finally you have 2x2 minus cosine. 2x2 and minus x1 to the 4 cosine of x2. Okay, so this is your Jacobian matrix. And now at each iteration, this matrix has to be evaluated at the current value of x1 and x2, and then inverted, and then multiplied by the vector function. So the update equation will be something like this, that the x1 at the new iteration and x2 at the new iteration is equal to x1 at the previous iteration and x2 at the previous iteration minus the inverse of this Jacobian evaluated at the previous x1 and x2 and times f. And f is here, when I say f, the vector f that you saw over there is f1 and what? f2. And the vector x that you saw in that update equation is what? x1 and x2 here, that you can see in here. These are x and f are in bold font, so it means they are vectors. So basically I have to bring these two equations and evaluate them at any what? x1 and x2. So let's do it and bring them all the way down here and finalize our update equation. So here, let me, by the way, bring this x2n upward as well, times. And here, I'll try to paste that guy right there. Good. And this guy also has to be evaluated at what? At the current x1 and x2. So if you want, you can say basically this whole thing be evaluated at x1 and x2. Okay, that makes life a lot easier. So here we go. Okay, this is your update equation. That x1 and x2 at the new iteration are this whole function, whatever it is, evaluated at the previous x1 and x2. Okay, so you have to keep repeating this until you converge to the solution for both x1 and x2, and you can expand it to as many equations as you want. And finally, as I said, limitations. So this method has several traps, several limitations. One of them is that the function diverges, which was something we had with other algorithms, secant method. And you can see the case here. If this curvature of the sigmoid is like that, then it's not perfectly sigmoid, but a function like this, basically, is like an inverse cubic function. As you can see, I start at I, okay, and then the slope will take me to I plus 1, slope takes me to I plus 2, 3, and instead of converging to the root, you see this is getting bigger and bigger and bigger, and I will diverge. I will ultimately go to positive or negative infinity. So this is divergence. The other thing you have is, now this first one is not really divergence, but let's say you started here at this point I, and you wanted to convert to this guy root on the right side, but well, when you started, the slope will take you to what? Take you to I plus 1, I plus 2, right? So you are being kicked from one point to the next, and ultimately when you are at I2, you start converging to what? To the root here. So if you have several roots, you have to try what? Several different initial guesses. Each one of them might or could converge to what? A new root. Okay, so you have to try, and sometimes some of those guesses will completely diverge. So the only thing in this method is you have to try a new initial guess, if it's diverging or it's not converging to what you guess it was the solution. And sometimes this third one is an interesting one. You're gonna get trapped. So here, that's the root on the left. You start here, and then you go, and then you get trapped between this I plus 1 and I plus 2, or somewhere in that range, and ultimately you will convert to this local minima. You will converge to the local minima, and you get trapped. inside that local minima instead of converging to the root. And this is a very common problem seen in steepest descent methods based on Newton-Raphson, which is basically called being trapped in a local minima. And there are so many different things in literature to avoid that. Okay, and we'll talk about those more advanced stuff later. So let's stop this video here, and thanks for your attention.